Good day, everyone. In today's lecture, I'll be explaining the concept of isotopy. Isotopy is a phenomenon that was explained by a scientist called Henry Moseley in 1900. This concept was used to modify one of the theories of John Dalton, which we call Dalton's atomic theories. The theory states that all atoms are alike in every aspect, but differ from atoms of other elements. According to Henry Moseley in 1900, he noticed that not all atoms of the same element are alike in every aspect. And in 1900, Henry Moseley gave us three phenomena, which are isobar, isotone, and isotopy. Isobar is a phenomenon that shows atoms of different elements possessing the same molar mass, while isotone is a phenomenon that shows elements or atoms of different elements or the same element possessing the same neutron number. In today's class, I will be explaining the concept of isotopy. Isotopy is a phenomenon in chemistry that shows atoms of the same element possessing the same atomic number but different mass number. Atomic number in an atom is the number of protons present in an atom, while the mass number in an atom, which is also called the nuclear number or relative atomic mass or atomic mass or atomic weight, is the arithmetic sum of the protons and the neutron number present in an atom. So in 1900, Henry Moseley noticed that not all atoms of the same element are alike in every aspect. Examples of atoms that are not alike in every aspect in their element are hydrogen. Hydrogen is an element with atomic number 1 and mass number 1, but it can occur naturally in three isotopic forms, which are hydrogen 1, which is called protium. We have hydrogen 2, which is called deuterium. This deuterium is what we have in formation of heavy water, which is D2O. And the third one is tritium, which we have in formation of ballistic missile or a bomb. Another isotope that we have is oxygen. We also have boron. We have chlorine. We have carbon. All these elements can occur more than a form naturally. So they are called isotopes. Now, in order to calculate the relative abundance or the geonormal abundance of isotopes of a particular element, there is a particular formula or equation that we use. And the formula is the relative atomic mass of any element that occur more than a form naturally is equal to the molar mass times the relative abundance plus the molar mass of the second isotope times its relative abundance. And if we have more than two isotopes, we are going to make use of this equation, where n belongs to natural number. And also, when we sum all the relative abundance, we must have 100% or a fraction of 1. So alpha 1 plus alpha 2 plus alpha n must be equals to 1 or 100%, where n still belongs to a natural number. So these are the two equations that we use in relating the relative atomic mass and the molar mass or atomic weight of the isotopic substances and the relative abundance, okay, of the isotopes in the element. Now let's check this example. The question says, the relative atomic mass of boron is 10.2. If the element occurs naturally in two isotopic forms, this and this, what are their geonormal abundances? Okay, the first thing we have to do is, here we have two isotopes. So I can easily say alpha 1 for isotopy 1 plus alpha 2 plus isotopy for isotopy 2 must be equals to 1. Then if I make alpha 1 the subject of relation, I'm going to have alpha 1 equals 1 minus alpha 2. That shows that anywhere I see alpha 1, I'm going to substitute 1 minus alpha 2. So I can recall now that relative atomic mass equals m1 alpha 1 plus m2 alpha 2. But the relative atomic mass of boron in the question is 10.2. So 10.2 equals, the mass number of the first isotope is 10. And from our equation, alpha 1 is equal to 1 minus alpha 2 plus mass number for the second one is 11 and alpha 2. So 10.2 equals, if I expand the bracket, I'm going to have 10 minus 10 alpha 2 plus 11 alpha 2. Then when I transfer 10 to the other side, it becomes minus 10. 10.2 minus 10 equals minus 10 alpha 2 plus 11 alpha 2. Then this will be 0.2 equals, this will give us alpha 2. So alpha 2 is equal to 0.2. Then I'll recall that alpha 1 is equal to 1 minus alpha 2. So alpha 1 equals 1 minus alpha 2 is 0.2. And alpha 1 is equal to 0.8. So these are the geonormal abundances of the boron. And if we want to have it in percentage, that shows that I have to multiply this by 100, and I multiply this by 100. And alpha 2 can be equals to 20%, while alpha 1 can be equals to 80%. And this is how we calculate or we solve questions under isotopy. Thank you very much. I see you guys in my next lecture. I remain Ajadio.